So this is from Eugene Paul Wigner in 1960, I believe. He says, the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious. And I really love this. It gets to the question a little bit of whether math is invented or discovered. Not going to debate that here. But I will say that the interplay between mathematics and the natural world is something that has fascinated and inspired me throughout my career, and indeed, it motivates our work at Metafold. I'll give a couple of examples. The first is Murray's law of branching. So this was formulated in the 1920s, and this is one of the first mathematical descriptions of how blood vessels branch. And there's a relationship between the central vessel and the branching vessels, but their radius. And what I like about this is that it turned out to be an optimization principle that applied much more broadly than blood vessels. And in fact, it contributed to the development of a whole mathematical theory of optimal transport. So how to move resources effectively through a network. So what I like is that we're taking an idea from biology, we're being inspired as mathematicians, coming up with a mathematical theory, and then that kind of takes on its own life and becomes its own line of mathematical research. Similar are L systems. These were again developed in the context of biology by Lindenmayer, 1960s. And similarly, he was looking, I think, at branching structures in nature, but the theory he put out with L systems ultimately contributed to the mathematical study of formal grammars. And formal grammar, you can think about it as a set of primitives and rules for generating some system. These go on to be applied to things like the Sierpinski triangle, which was much earlier, but I find it fascinating that this idea rooted in biology can be then applied to mathematics and again goes on to become a bigger mathematical theory.